Hi, everyone. Thanks for tuning in. I'll start by introducing myself. I'm John Adeojo, founder and chief data scientist at Data-Centric Solutions. Today, we're going to be diving into the topic of LLMs, specifically how to fine-tune your large language models on a budget. Now, there are some really powerful techniques that are available now for fine-tuning large language models. Just to give you an insight, large language models, given the size of the things, tend to cost a lot of money to fine tune. And, we know that OpenAI spent over $100 million on training ChatGPT or GPT-4 from scratch. That's the figures that were quoted. And even if you're not training from scratch, it can be really expensive to fine tune even smaller models at, let's say, 1 billion or even a few hundreds of millions of parameters. Researchers from Microsoft have come up with some methods that we can use to fine-tune models with limited infrastructure and cheaply. So I anticipate this is going to be useful for anyone that is, if you're a hobbyist, if you are a student, if you're even a startup founder and you want to get a prototype off the ground really quickly, keep watching. This video is probably for you. So let's just talk about the demand for bespoke large language models. So since the rise and success of ChatGPT, we have seen a surge in demand for bespoke large language models. A lot of this is to do with the fact that companies have their own private internal data sets that they often want to perform some type of automation on. There is also the issue of data sharing. So a lot of companies don't want to share their data with OpenAI and leverage the technology they have, which leads them down to the path of, okay, can we train our own large language model? Which the answer is usually no. And then the next logical step is, okay, can we use a pre-trained model and fine tune it for specific tasks we have within the business? And the answer to that is usually yes, you can. However, it does come at a cost. So the method we will explore today is called a PEFT method, which is parameter efficient fine tuning. It basically allows you to fine tune a smaller version of the model. And I'll get into more details about PEFT, about the specific PEFT method a bit later on in the video. Let's just talk a little bit about the case for fine tuning models. Why do we want to fine tune models in the first place? Well, I'll give you a scenario. I have previously worked at a bank where we employed an analyst to track customer complaints and do some reporting on those complaints. That analyst would spend several days, a month, manually moving the complaints into an Excel spreadsheet and then manually categorizing those complaints. So going through line by line, reading what the complaint was, categorizing it just for downstream reporting. Obviously, as you can imagine, the task was tedious. We had thousands of complaints. The analyst trying their best would often make mistakes, as you would. And yeah, it was something that consumed a lot of time and resources. Now, at the time, I wanted to implement a model to just automatically categorize this. And with the limited resources we had, we were limited to doing something tree-based. So we're looking at doing using an XGBoost, for example. But now the platforms and the infrastructure available means that you could actually have leveraged a large language model and fine-tuned it on that task of customer complaints classification. So the video today, the demo today, will be how I cheaply fine-tuned a large language model for customer complaints classification. And this is specifically for financial services. So let's talk a little bit about the data set and then we can go into more details. So I'm just going to pull up the data set. So the data set I've used for fine tuning comes from the Consumer Financial Protection Bureau. And it's an open data set. You can pull this yourself from Google Cloud using Google BigQuery. It's provided under their open data sets. Or you can just go directly to the Consumer Financial Protection Bureau and pull the data straight from source, or you can use the data set that I have uploaded to Hugging Face, which is open and available for you to experiment with as well. Just follow the link, and I will provide all the links to the resources you need to replicate this in the description. So as you can see, there is a sub issue, which is our categorization, and it's a high level view of the actual complaint. And then we have a series of customer complaints here, or consumer complaints. And these are all related to financial products or financial services. So I'll just give you a second to have a look at this. We have around 123,000 rows of this data. This is the type of task we're performing here is a multi-class classification task. And I believe we have over 200 individual categories. So over 200 different sub-issues that we can classify this data into. So you can imagine if you were you're employed as an analyst at a bank and you had to do this classification, it could become quite tedious to do this, to actually read each complaint and then decide which category to put that complaint in, because you need to do this for downstream reporting often. Let's talk a little bit about the hardware available, because the hardware is obviously important if you're trying to fine-tune a large language model. So I did this entire thing in a Google Colab, and anyone that's used the Google Colab before, you might know that the A100, which is the most performant GPU, often is unavailable. So what I had available to me was I think the next best thing, which is the V100 GPU, which has 16 gigabytes of RAM. All in all, it's pretty good for something that's available to the everyday consumer, and it's pretty inexpensive. So Google charge out renting these GPUs at approximately $9.99, so $9.99 per 100 compute units. I'll get into more about how much it costs to fine-tune this large language model a bit later on in the video, but that's how much you can rent out your GPU if you're using a Google Colab for yourself. So remember, they do charge at compute units. So 100 compute units is $9.99. You can pay on a monthly basis, or you can there is a pay-as-you-go option as well that they provide. And if you find yourself using over that 100 compute units, you can simply pay the same price for 100 more. All right, so let's talk about the large language model itself. So the PEFT method works on a pre-trained model. Just to illustrate the power of this, I wanted to select the biggest pre-trained model that could fit into the 16 gig of RAM. And the model I chose for this was the RoBERTa model. So it's the RoBERTa XLM model, which has roughly about 563 million parameters, which is very large. If you try to fine-tune that on a GPU without doing any kind of augmentation, you might find that the GPU does crash, especially a GPU of this size of just 16 gig of RAM. So I think it's a good model to demonstrate the power of the PEFT method here, the parameter efficient fine-tuning method. So let's talk about the fine-tuning itself and the PEFT method we used for fine-tuning. The method used is called LoRA, or low, which stands for low rank adaptations of large language models. So low rank adaptations of large language models. The method takes the existing pre-trained model, which has around, what did I say, 563 million parameters, which is fairly large, not the largest large language model out there, but large enough for given the amount of memory we have on our GPU. It freezes the existing large language model. So freezes the 563 million parameters, and then it injects a trainable lower dimensional layers into that model. So those models are obviously lower dimensional and have a lot less parameters. But what they found is, using the LoRA technique, the researchers actually found that the performance of fine-tuning with LoRA is preserved, and LoRA has also been shown to reduce GPU memory consumption by a factor of 3 compared with just your standard fine-tuning. If you're curious and you want to get more into the paper itself, you can here, and I will provide a link to the paper, but there is also a link to the paper in the technical blog that will accompany this video. So how do we actually apply, how do we go about applying LoRA if we want to fine-tune a large language model? Now, there are a few steps before doing this, and I won't go through all of the details because the Colab is going to be available as well. But I will skip straight down to how we apply LoRA to our base RoBERTa model. As you can see, there are two frameworks that I have used here to apply LoRA. So the first one is the transformers from Hugging Face. And if you're not familiar with the transformers library, I implore you to check this out if you are serious or interested in anything to do with natural language understanding, generative AI, conversational AI. It's an amazing hub and hosts lots of open source models that you are able to experiment with for free, pretty much. And some of the latest models are actually on the hub as well. So you can get access to Llama 2, Falcon, and some of the older classic models like BERT, for example. There are thousands of models in the hub and thousands of researchers, experimenters, hobbyists fine-tuning models and uploading them on the hub for you to use and experiment with yourself. So that's the transformers library. That's from Hugging Face. And you have this auto model for sequence classification, which just allows you to pull the pre-trained RoBERTa model straight from Hugging Face with all of the weights initialized. The second bit here is the PEFT model. So this is where this is a wrapper that it's, I believe, on top of Hugging Face transformers that allows you to use the LoRA configurations to start actually transforming or getting those lower rank representations for your underlying transformer model. Following that, the implementation is actually quite simple. You want to set your configurations. So I've assigned this to config here using the LoRA config. And then it's literally about going through and setting up each argument in the LoRA config, or setting up each parameter in the LoRA config. So I'll talk through these parameters really quickly just to give you an explanation of what each one does. So the first one is task type. And it's obvious that our task in classifying customer complaints is just sequence classification. So that's specified here as sequence classification. There are other tasks that you can do, and I'd implore you to check out the LoRA documentation for just to see the range of other tasks you can do, Hugging Face have some great tutorials on how to use LoRA for different types of tasks, including token classification, for example. The next two parameters here are parameters specific to the LoRA approach itself. So these are what we'd call hyperparameters. The first one, R, is just a hyperparameter named LoRA attention that which kind of affects the scaling, and the second one, LoRA alpha, also impacts the scaling. So these are just how these hyperparameters are. They impact how LoRA creates those low rank representations. The next one is pretty important. This is the target modules. So the target modules specify which layers in your underlying model that you want to actually apply those transformations to. So if you know anything about transformers, or if you've read the text, you'll know that query and value are part of the attention blocks for transformers, or the attention heads. So I've specified here that the LoRA transformations should be applied to the attention heads by stating query and value. The LoRA dropout, again, this is pretty standard to deep learning, and you put dropout layers there for the purposes of model regularization. The bias is simply just the bias for the LoRA layers, and then modules to save. This is important as well. These are the modules that you want to make trainable within your underlying architecture. So within the RoBERTa underlying architecture, and for us, this is the classification head, because we're tuning this to a different task. So we want to make this trainable. The next step is just setting up the model itself, and this is pretty standard for a Hugging Face transformer model. So all I'm doing here is calling that RoBERTa model from the Hugging Face hub. Further up in the script, I've assigned this to the location, or the ID, the model ID for RoBERTa. Setting the number of labels. So we have, I believe it's probably around, I'll just double check, but how many classes do we have? Yeah, so we have around 204 labels. Yeah, label for the first example. No, that's not correct. It's not in this notebook, but we have over 200 labels. So the number of labels is just simply set to that ID to label and label to ID. So if you don't set these parameters when you're training your Hugging Face model, what will happen is your model will just return the encoded labels. So for example, in our case, if we go back to the actual complaints data, what we want to return is, if we give a consumer complaint, we want to return a string from the model. That's what's going to be useful for us. That's the classification. However, if you don't set label to ID and ID to label, what happens is your model will take the string and just return an encoded output, which would just be an integer. It's not very useful for us. So that's what that parameter does. It helps us return the decoded output, so to speak. Ignore mismatched layers, mismatch them sizes, set to true, because I think the original classification model, the RoBERTa model, is designed to classify just 2 or 3. I think it's a binary classifier. I could be wrong on that, but essentially the original RoBERTa model is designed to classify less outcomes than the model we are currently training. So that just prevents any errors when you're running this. After that, you just simply run and you have your model and LoRA configuration set up. So let's just talk about this output for a second. So as I said, you get low rank representations of your individual, of your specified transformer layers, right? So this is represented here. All parameters, these are all the frozen parameters that we talked about before. That is 562 million. So that's the original RoBERTa model. With the LoRA transformation, we have reduced that down to just 4.1 million trainable parameters. And, we've got a percentage here. That's just 0.73% of the original parameters. It's really remarkable that these researchers have essentially shown and demonstrated that we can still fine-tune a model with a lower number of parameters and achieve a similar level of performance than if we fine-tune the entire model. That's pretty fantastic. I'll talk briefly about how we initiate the model training itself. So there are actually a few parameters here when we are initializing the model training, or when we're running the training job, that we can set to manage our GPU usage as well. And it is important to set these. There's always a trade-off when you're fine-tuning transformers between GPU usage and the speed of training. And it's important to get that balance right. I'll get into more details about specific parameters for that a bit later on. So first of all, I'll just talk quickly about the metrics. So the metrics I've chosen to assess performance of this model are F1, recall, accuracy, and precision. Now, I'm not going to go into too much detail about what these metrics are in this video. I have a technical blog explaining much better than I could in the 2 minutes or 3 minutes I have what these metrics are and why they're important and when to use them. So check that out. I will link that in the description below if you're indeed interested, or maybe I'll put it in the comments. So this is trainer itself, and again, this is available from the Transformers library. It's just an API that you can leverage from their library. There are a lot of parameters in here, but I'm going to go into the ones that are specific for managing GPU usage, which is going to be key if you are going to fine-tune your own large language model with limited infrastructure. So when I say GPU usage, what I mean is GPU memory consumption. So let's talk a little bit about those parameters. So the first one is the per device train batch size. So, you can imagine your GPU allows you to compute many calculations in parallel, and you can decide the batch size of each of those parallel batches of calculations that your model's running, that your GPU is running when training the model. So if the lower you set this per device train batch size, obviously the less memory the GPU needs to use, but you do sacrifice training speed for this. There's a balance. Setting this to higher values will allow you to train your model faster, but it will consume more of that GPU memory. And if you don't have enough, your model will crash. Your training process will crash. So be mindful of that. The next step here in terms of GPU memory usage is the per device eval batch size. So setting this parameter dictates how many samples are processed on each GPU core for evaluating your model. So, this is a supervised learning task, and at each training step, after a certain amount of training steps which you can specify, the model at the state at which it is will be evaluated on your evaluation data set. And it's a good way to track how well the model is fitting to the data, or how well it's generalizing to the data. Now, if you increase this number, you will increase the speed of evaluation and therefore the speed of overall training, because evaluation is part of that training step, but it is at the expense of GPU memory usage again. So that is something to be aware of. The next one here is the gradient accumulation steps. Now, you'll have to follow me on this because this is a little more involved than the others. So usually when you're updating any type of deep learning model, when you're fine-tuning, training, whatever you want to call it, when you're doing that process for a deep learning model or transformer, there are a few steps, right? So the first one is the forward pass, where your weights are initialized, and then a prediction is taken from your network and compared to the label, and your loss function, or your loss over the network, is calculated. The next step is using some kind of optimization process where you first of all determine the gradient of that loss function, and then the idea is you want to minimize that gradient, and that is what we call back propagation. So what gradient accumulation does is, apology, I'll take a step back. So once in minimizing that loss function, you usually calculate the gradient and adjust the weights in the model by some measure of the gradient. And this can be done after every forward pass of the network. So what gradient accumulation actually does is it postpones the updating of the weights by the gradient by the specified number of steps, so the specified number of forward passes through your network. The idea here is that you allow your network to see a larger batch of samples before updating the weights by the gradients. So why it's called accumulation is, once you have that forward pass through the network, the gradients are accumulated instead of being used to directly update the weights straight away. So they're accumulated. So if, for example, the gradient accumulation steps are 2, you have 2 passes, and pass 1 sets the gradients aside, pass 2 sets the gradients aside and accumulates those, and then applies the weights at that stage after that. It does allow you, so the advantage of this is it allows you to have a larger effective batch size. So what does that mean? Effectively, your network sees more samples of the data before it updates the weights. So you can actually measure the effective batch size by multiplying the gradient accumulation steps by the per device train batch size. So in this case, 2 times 8, which is 16. So our effective batch size is 16. And why this is GPU saving, if we were just to set our per device train batch size to 16, we would use more memory than if we used an effective batch size, if we use the gradient accumulation method here. So you can effectively get the benefits, reap the benefits of training on larger batch sizes without paying the cost in memory or on your GPU, without paying that cost in RAM. I think the gradient accumulation process probably does add some more steps to the training process, which would make it a little bit slower compared to just having a larger per device train batch size. The last one is the FP16. So this is mixed precision training. That's what it stands for. So full precision is at 32 bit. That's full precision training, and half precision is at 16 bit. So essentially, when you set FP16 to true, what you're able to do is train the model using both 32-bit and 16-bit precision, which actually speeds up some of those calculations. So effectively, what you're doing here is you're getting a bit of speed at the cost of memory. Why is that the cost of memory? Well, if you use mixed precision training, because of how the calculations are done, because you do some calculations over the network in 16-bit and some in 32-bit. What happens is the training process needs to store the model in 32-bit on the GPU, but also it needs to store the model in 16-bit, which leads to you getting roughly about 1.5 times more GPU usage from just the model storage. So more GPU RAM usage just from the model storage alone. So you want to be careful with this parameter. It will increase your training speed. That's the idea behind it, but it is at the cost of RAM on your GPU. So be aware when you're doing that. The other steps here, the other parameters here are really just about deciding how many steps to train the model for. So you can do this on a number of epochs. I've chosen to do it on a step basis, but essentially this is how many forward passes through the model you take on your training process, so how many different samples are being passed through the model. Now, the max steps here has been set to 49,000. And then the evaluation steps. So this determines at which step or after how many steps the model does the evaluation process. Now, obviously, you do want to evaluate your model. It's good to be able to track what's happening throughout that training process. But you have to balance this number out, because the lower this number, the longer your training process is going to take, because it needs to pause and then do the evaluation, which takes time to do anyway, and it will add to the overall length of time of your training process. Login steps is just, recording the results of that evaluation, and save steps is saving the state of that model after a particular after a particular number of steps. Now, here's a bonus tip. If you haven't already looked into weights and biases, I would implore you to do that. Weights and biases works really well with the trainer API from Hugging Face Transformers. And what it does is essentially tracks your training process over the time you're running it. And there's a free tier available to you. You probably won't eat into it. So I implore you to leverage weights and biases, and I'll go into the training report to show you what that looks like. It's really something fantastic. Okay, so I did run this earlier and the model ran for approximately 9 hours, which is a long time. And you can see all of the training steps here. We didn't quite get to a model that I would describe as usable in production. The performance seems to, first of all, I didn't believe the model actually converged. There's still a few more training steps that I think we could have gone for, but that would have required me to run the model for quite a long time. And I'll show you what that looks like on weights and biases. And you can see that we've got a pretty low F1 recall and precision here. But in either way, I've still published this model for you to play around with yourself, and the checkpoint is available publicly. So if you do want to fine tune this yourself and you have more resources and more time, you're welcome to do that from my checkpoint. So let's just take a look at the weights and biases report. I'll just pull that up. So this is a weights and biases report for the model run. And what you can see there is it's pretty fantastic. It tracks everything. So, you know, our accuracy has been tracked, our precision, F1, recall. And yeah, check this out. So check out the evaluation loss. There is not really any sign of this flattening out yet, which means that we could probably go for a few more runs. And it's the same for the training loss as well. So if I just go to the next page here. Yeah, so you can see that the training losses, it doesn't seem to have converged as of yet. There's no sign of that loss just flattening out. Yeah, there's probably a lot more performance gain that we could get from this model by running it over a much longer period of time. But you know, with the limited hardware, you do sacrifice GPU memory usage for training speed, which means that you'll be waiting a long time for this model to converge, and you'd have to, you know, spend the resources to do that. Okay. So getting back to fine-tuning the model, after running that, I just deployed this model to the Hugging Face hub, and that's pretty easy to do following the API. I won't go into the details of the deployment here, but if there is demand for it, I'll make another video on how to do that and how to set up your own Gradio app to deploy your models and have some nice prototypes to show prospective clients, or just as a cool data science project that might make you stand out for your job interviews. Before we move on, I just want to show you some of the diagnostics for the GPU usage itself, so you get an idea about the training process. So if we go to the GPU memory allocated, we can see that throughout the training process, we pretty much stayed at around 87% of the memory. So that's enough such that, you know, we could train our model for 9 hours and not have the process crash, which is what you want. The worst thing is when you've trained the model for a period of time and then you come back and it's you go away and do something else, you come back and it's crashed. So it just goes to show you that the methods we were using were effective to prevent that happening. The uptick here is actually quite funny because I wanted to do a training assessment. I wanted to test the model on a holdout data set that I had separately. I had about 30,000 observations, but you know, even the inference process takes up some memory usage. So you can see that uptick there, and you know that I gave up on that in the end because it just was taking too long. I lost patience with it. And I guess the nice thing about weights and biases as well is it kind of gives you all these interesting statistics about power usage and GPU power usage, even GPU temperature, which is quite interesting. I haven't really seen anything like that provided elsewhere. So yeah, again, it's another selling point for weights and biases. Okay, so let's talk a little bit about the cost of this thing. So as I mentioned, I ran this training process for 9 hours. The GPU usage across that 9-hour period was probably, if we round it up, around just under 15 gigabytes of RAM. As I mentioned before, the Google Colab charges you out to rent the GPU at $9.99 per 100 compute units. Now, I couldn't find anything specifically from Google how they define their 100 compute units, but in general, what I found was that 1 gigabyte of GPU memory multiplied by 1 hour of usage is equal to 1 compute unit. So based on that math, the number of compute units that I used for this training process was around 135. So 135 compute units, and at a price of $9.99 per 100, I spent approximately $13.49 on training this model. Now, granted, it is not free, but it is still relatively cheap to train a model. And I anticipate maybe to get this model to converge, you would probably need to spend maybe 4 or 5 times that much to get a prototype that you would be happy to put in front of clients, or you would be happy to roll out for a test across your organization. However, that is significantly less than it would be if you didn't use these parameter efficient fine-tuning methods and the GPU memory saving techniques that I've showed. So I guess that's the end of the demonstration today. I hope that you managed to learn something from this today, and I hope that's given you the confidence to get out and maybe go open up your own collab and try to fine-tune a model. You can use a smaller model, which will probably be cheaper because it will take up less GPU RAM, and combining that with LoRA or any other parameter efficient fine-tuning method would be a fantastic move for your, just to practice some of these ideas. So there are a few things for anyone that's interested. The Google Colab is going to be available in the link in the description of this video. There's a technical blog that accompanies this video as well. That's going to be available in the description as soon as I'm able to publish that. The model itself and the application is available on Hugging Face. So the model checkpoint is available. You can download that and train from that checkpoint if you want. Just lastly, before I forget, I did say that I would demo the model. So let's just get into that. This is a Gradio app I've developed, and what you can do is essentially launch a financial complaint. So let's say something like, I did not receive the credit card I ordered post. I contacted the bank, but they have not been able to assist. It's taken too long to get anybody to help with this issue. It's a bit of a random complaint, and it's just something I've thought off the top of my head, but just to demonstrate how the model works, we'll submit it. It's processing that. Problem getting a working replacement card. So that's not quite there. It's close, but it's not quite there. And you can see why that is. We already showed that the model hasn't quite converged yet, and there's probably a lot of training or fine-tuning that needs to be done before we get something that is performant to the extent that we want it. But it's pretty good. It's identified that, you know, we're talking about getting a card. It's identified that it's something to do with that anyway. So have a if you want, feel free to play around with this yourself and, you know, have a play with it and let me know your thoughts on the app itself and the use case. Just to show you where the model checkpoint is, I will go back to, so the one you want is, that's checkpoint 2. So this is the one you want, the XLM RoBERTa Large LoRA Consumer Complaints CFPB 49K. So that's 49K because this is the one I ran over 49,000 training steps. So that's available for you. It's a public model. You can grab that from Hugging Face and play around with it yourself, or, you know, create your own app off the back of that. Thank you for tuning in. I know it was a bit of a long one today and probably a bit technical. It would be great to get some feedback. And if you like this, please feel free to share, like, subscribe to the channel. It really helps us out. You know, we're a new channel and we're trying to grow. So we really appreciate your support. Comment in the comment section about anything that you would like to see me talk about or do next, or anything that you'd like me to demo or explain. Thanks for tuning in.